Hello, I'm Xipeng from Chinese Academy of Sciences. Today, I'm going to introduce our research work, Cooper, testing the binding code of scripting languages with cooperative mutation. It's a joint work with researchers from Tianjin and Pennsylvania State University. As we all know, scripting languages is very useful and powerful. It's easy to learn and develop. Nowadays, scripting languages are integrated into document processing programs. For example, JavaScript code is integrated into PDF and HTML. VB code is integrated into Office document. In these programs, embedded scripts code are usually used to manipulate the content elements of a document. Vulnerabilities in this embedded scripting language are very dangerous. Attacks can exploit vulnerabilities in these programs to execute basic code and take control of the system. And every year, many vulnerabilities are discovered in embedded scripting system. So it's essential for us to design an effective method to find bugs in embedded script code. First of all, let's look into the internals of document processing programs. The input contains two parts. Native objects represent figures, texts, and even annotations. Script code contains scripting languages like JavaScript code here. The program has two components to process inputs. They have native code to handle native objects and use language interpreter to execute script code. To connect the two different components, these programs usually have a binding layer to do translation. However, the binding layer is too complicated to be 100% correct, and the bugs are inevitable. Previous work, like FiveCardinal, only focuses on mutating the script code, which may miss complicated bugs. Here is a heap overflow bug from Adobe Acrobat. So attacks can use this vulnerability to run arbitrary code remotely. It's so severe that we were awarded with $2,500 bounty for this particular vulnerability, and it has been fixed. Then let's see how to trigger this vulnerability. First of all, in native objects, we must insert one extra element into funds with array. Then in script code, we must utilize JavaScript code to change the zoom type of the document to RFW. So as you can see, to trigger this vulnerability, we must mutate both native objects and script code. And a traditional one-dimension mutation further cannot find this sort of vulnerability. Inspired by this vulnerability, we wanted to design a new solution to discover this sort of vulnerabilities related to both native objects and the script code. Our solution is cooperative mutation. We mutate both native objects and script code in cooperative manner. So we come to the problem, how to achieve cooperative mutation. First of all, we need to infer the relationship between native objects and the script code. And then we use the inferred relationship to get a mutation in both sides. Specifically, if a scripting API has a potential connection with some objects in a document, we will assign these objects a high priority for mutation. Otherwise, we just randomly choose some objects for mutation. To achieve cooperative mutation, there are several challenges to be solved. The first challenge is how to infer the relationship between native objects and script code. Once we have the relationship, we need to solve the second challenge, how to use the inferred relationship to get a mutation. However, when we solve these two challenges, we encounter a new problem, that there are so many native objects. That means we will have a huge search space for inferring relationship and getting mutation. It's not doable. To solve this problem, we need to reduce the search space. So how to reduce the search space? We plan to categorize all native objects into different classes according to their semantic feature. So let's come to our challenge zero. How to class the native objects into semantic similar classes. Then let's figure present overview of our solution. It has three components. The first component is object clustering. It clusters a large number of native objects into a small number of object classes according to their semantic feature. Once we have the object classes, we need to infer the relationship between object classes and scripting APIs. This is the purpose of our second component, relationship inference. This component utilizes a statistical method to infer the relationship. Finally, we come to the third component, relationship-guided mutation. In this component, we use the inferred relationship to guide mutation. Then I will show what components in detail. The first part of our solution is object clustering. An object usually consists of some attributes. Each attribute is a pair of name and object. Through our operation, the name of object usually carries some semantic information. So in the first step, we class the objects with their names. We just put objects with different needed names into different categories. However, in some code cases, clustering objects by their name may not be correct. To get a fine-grained object classes, we split and merge object classes with their attribute similarity. Specifically, we use that formula to calculate the similarity between object classes. If the similarity is less than a threshold value, we split a big class into several small ones. If the similarity is greater than a threshold value, we merge these small classes into a bigger one. Through these two steps, we finally get a fine-grained object classes. The second part of our solution is relationship inference. We take two steps to infer the relationship. In the first step, we do execution logging for all samples and divide them into two sets, success set and failure set. Specifically, we prepare a testing code and insert the testing code into the orange sample. Then we use the application to open a new sample. If the testing code successfully found related elements, we put the orange sample into success set. Otherwise, if the testing code cannot find related elements or produce error, we put the orange sample into failure set. So through this first step, we have divided all samples into success set and failure set. After we divided all samples into success set and failure set, we use statistical method to infer the relationship between object classes and scripting API. And finally, we get a relation map. As you can see from the map, the success rate is the percentage of samples that contain this class of objects in the success set. The failure rate is the same percentage in failure set. And the difference is the difference between success rate and failure rate. We think the different value represent the strength of the relationship between object class and scripting API. In the second part of our solution, we have got the relationship map between object classes and scripting API. In this part, we will utilize the relation map to guide a mutation. First of all, we determine target API group, and then we take a traditional method to generate a script code. For native objects, we get a seed sample and select objects in this sample for mutation. Specifically, we refer to the relation map and design algorithm to calculate the mutation probability for each object in the seed sample. In general, the mutation probability is positively correlated with the strength of the relationship. Then we select some objects with higher mutation probability and mutate selected objects in 3 mutation strategies. Finally, we synthesize the mutated samples and script code together and produce the final input. So let's work over our solution. For implementation, we have developed Cooper in 4,000. We developed Cooper in 4,300 lines of Python code, and Cooper has utilized some open source library. In particular, it uses PDF2 Python library to parse PDF format, use zip file and XML Python library to parse Word format. For scripts generation, we utilize Domato and improve it with block level template. Cooper currently supports two formats, PDF and Word. It's notable that Cooper is extensible and portable. You can easily add some new features to Cooper and can also apply Cooper to other document formats with limited manual efforts. Then I'm going to talk about Cooper's evaluation. We apply Cooper to real-world programs to find bugs, and we compare the capabilities of bug finding and edge finding in different configurations and tools. We apply Cooper to three real-world programs, Adobe Acrobat, FoxReader, and Microsoft Word. In 4 months, we totally found 134 previous unknown bugs and got 33 CV numbers, and 59 bugs have been fixed. We were totally awarded with $22,000 bounty. All these vulnerabilities are related to 90 API in 11 object classes. To fully understand the capabilities of Cooper, we prepared 5 configurations. Cooper 4 is the full-featured configurations. It utilizes inferred relationship to do cooperative mutation. Cooper random doesn't use any relationship. It just randomly chooses some objects and scripts code for mutation. Cooper object only mutate native objects without any mutation for scripts code. On the contrary, Cooper script only mutate scripts code. The last experiment is conducted with Domato. Since Domato is originally designed to test the general JavaScript code, we add a JavaScript template of PDF and a VBA template of Word document. We applied different configurations on Adobe Acrobat and recorded the bug finding history in 1 week. As you can see from this figure, Cooper 4 found 18 bugs in 1 week, which is the most among all configurations. This result proves our concept that cooperative mutation is essential to find bugs in binding code. We also do experiments on FoxReader. The result is similar to Adobe Acrobat. Cooper 4 always found the most bug. To test the edge finding ability, we apply all configurations to Adobe Acrobat and record their edge finding history in 1 week. We record both scripts coverage and native coverage. As you can see from these two figures, Cooper 4 can find the most in both types of coverage. We also do edge finding experiments on FoxReader and Microsoft Word. Their results is similar to Adobe Acrobat. Cooper 4 always found the most coverage. Their results can also be a proof of our concept. Cooper cooperative mutation is essential in finding bugs in binding code. In conclusion, we propose cooperative mutation to test the binding code of scripting languages. Our system, Cooper, found 134 bugs in Adobe Acrobat, FoxReader, and Microsoft Word, and received 33 CV numbers and $22,000 bounty. And Cooper is now open sourced on GitHub. Thanks for listening. I'm ready for questions.